Welcome back to our last video for College Algebra. Today we're going to be looking at section 7.3, which talks about systems again, systems of nonlinear equations and inequalities containing two variables. So we skipped over 7.2 if you're reading through your textbook, just because we weren't going to deal with three variables in this class, but we're still going to cover this last section before your final exam. So let's go ahead and jump right in. Our scripture for today says, I press on to reach the end of the race and receive the heavenly prize for which God, through Christ Jesus, is calling us. And while we're pressing on in this class towards a very specific goal of our final exam and completing the class and hopefully passing and doing the best that we can, this verse just reminds us of a higher calling and a heavenly calling for which Christ Jesus has called us. That's not to be forgotten in the midst of all the work and the trouble and the studying for finals that I know you're experiencing right now. So just know that as you approach the end of this semester, I'm praying for you. I hope that your studies go well, and I wish you the best. Let's go ahead and get started. We're going to start with a lot of the same tools that we've been using, or that we used in 7.1, and we're just going to see those tools get used more, just sometimes with a plus or a minus sign now, is the main difference between the two sections. So the first intersection type that it gives us is a line and a parabola, and it shows you here in these three examples they could not touch, they could touch once at a perfect tangent line, or they could touch twice, and those are pretty much the only options. And so we're going to solve it, and we're not going to be surprised if we get two answers. And so this one gives us the idea that we're allowed to use substitution, and so what I'm going to do is pick the easiest variable to isolate, which I think is going to be this y right here. And so I'm going to take this first equation and I'm going to write 3x minus y equals negative 2. And I'm just going to try to get that y by itself. So 3x equals y plus 2. I added the y to both sides. And so y is equal to 3x minus 2. Now why I did that is because I'm going to take that y and plug it into my other equation, this one. So we're going to take this y value we have from this equation and plug it straight in where we see the y. And so what we'll be left with is 2x squared minus parentheses, because we're plugging in a whole equation, 3x minus 2 equals 0. So it might feel a little bit like the composition of functions where you plug the function into a function. That's kind of similar. We're plugging a whole linear equation into another equation that contains a y. And then we're just going to solve this. So this looks like 2x squared minus 3x minus 2 equals 0. And this looks like one of the types of equations that we would use grouping for, because it has an a and a c that aren't equal to 1. And so remember, when you group like that, you say a times c equals 2 times negative 2 is negative 4. And you say, what are the factors of negative 4 that turn into 3? And it looks like negative 4 and positive 1 will turn into that negative 3 in the middle. And so we break apart that negative 3 into those two terms. This is a review from grouping. I know it's the last day of your videos, but if you need help with grouping, go back to the grouping video from the quadratics, and I think 2.6, maybe 2.5. There was a whole section on grouping, and we practiced it. So minus 4x plus 1, x minus 2 equals 0. And then we're going to see what factors out from this set of numbers. It looks like in the first two terms we have a 2x, and in the second two terms we just have a 1. And so on the outside we'll have 2x parentheses, looks like x minus 2. If we divide, remember the green arrows is division. And over here we'll have a positive 1 outside of x minus 2 equals 0. And then what we'll do is factor out those x minus 2's in the same way we just factored out. We're dividing by x minus 2. And we get 2x plus 1 times x minus 2 equals 0. And we can solve both of those. And so when you solve both of those, you get x is equal to negative 1/2. Remember, we solved it by setting each factor equal to 0 using the zero product property of multiplication. And x equals 2. And it looks like we're going to have two solutions. But because this is a system of equations, just like the last section, 7.1, we need to find our y values. So I'm going to grab the easiest formula I have, which looks like it's highlighted up here, and I'm going to bring down the easiest version of the formula that I can find to find y. And so I have this other formula, or this linear equation that says y equals 3x plus 2. And so I'm just going to plug both of those x's in to that equation. And so for the first one, we're going to have y is equal to 3 times negative 1/2 plus 2, which means y is equal to negative 3/2 plus 2, which means y is equal to, that's like 2 minus 1.5, so just a positive 1/2. And the second one's probably a little easier. Y equals 3 times 2 plus 2, which just means y equals 6 plus 2 is 8. And there we have our two solutions. Our two solutions, if we put those in point format, are going to be 2, 8 and 1 or negative 1/2, 1/2. And so if you zoom out and look at this whole problem, this looks like one of the C ones up here. It looks like a graph of C where there are actually two solutions to this intersection of a parabola and a line. You can pause that if you want to look at it. I know it's a pretty long problem. That's why we gave you the whole page to do it. These are good problems to practice and make sure you've mastered before moving on to the next one. All right, let's move on to a circle and a line. So this top equation is a circle, and this bottom equation is a line. And the intersection of a circle and a line can be no intersection, one intersection, or two, just like a parabola. And we're going to use the same skill that we used a second ago. We're going to use substitution. And here it looks like the easiest substitution to use would probably just be that x hanging out by itself. And so I'll say, I'm going to rewrite this bottom equation to be x equals 3y minus 10. I just moved the 3y over. So remember, as we're doing these types of problems, there's the equal sign lined up. These two equations are the exact same linear equation, just written a little bit differently. This blue equation is a different equation for a circle. Okay, so now I'm going to substitute that x into my equation for a circle. So I have x squared plus y squared equals 10. But x isn't going to be x. It's actually going to be that red equation I just solved for. And so I'll say 3y minus 10 squared plus y squared equals 10. And we're going to solve that for our solution. And so here we go. First thing we need to do is we need to FOIL. Be careful with foiling. You cannot just distribute that squared. This is a lesson we've had in almost every single section so far. So 3y times 3y is 9y squared. Negative 10 times 3 is negative 30y. And you'll have two of them, so that's negative 60y for the outside and the inside term of the FOIL. Plus 100 plus y squared equals 10. That was a FOIL that resulted in these three terms. Now if we combine like terms, we get 10y's on the left minus 60y plus, I'm going to move that 10 over, 90 equals 0. Now before solving this, because that looks like an ugly quadratic, but it has a 10 in common, so I'm just going to divide both sides by 10 to make it a much easier quadratic to solve. So y squared minus 6y plus 9 equals 0. That quadratic looks like it factors nice and neat. What are the factors of 9 that add up to negative 6? Negative 3 and negative 3. So we have x minus 3 equals 0. And so what are the factors of, or what are the zeros that each of those factors give us? Well, this gives us x equals 3, and this gives us x equals 3. So it looks like we might only have one solution because all we have is 3 being our x value. Oh, whoops. This was Look at this equation line. Those variables are y's. You might have yelled at me if you were saying, hey, I thought we were doing y's right now. We are. I don't know why I changed those to x's. We're working in y's right now. So y equals 3. And then again, we don't have a full solution because we need two numbers. We need the x number and the y number to solve for this. So I'm going to grab the easiest equation we have, which I guess looks like the top one. Oh, is there another? Oh, there's a linear up there. There we go. This one looks like the easiest equation out of all of them to solve. And so that's what I'm going to use. And I'm going to say, take my 3. So my equation up there is x minus 3y equals negative 10. So I'm going to take that y answer that I just found, my solution y value, and I'm going to plug it in for y. So x minus 3 times 3 equals negative 10. X minus 9 equals negative 10. If you plus 9 to both sides, you get x equals negative 1. And so we have solutions. So our solution or our point where these two graphs intersect is negative 1, 3. And so from the pictures, this looks like the middle type. The type where there's one solution. It's a perfect tangent line to the circle. If you need to pause that and practice again or look at it, feel free to. We'll move on to try it 3, which is just another two types of graphs that are going to intersect. So here we have, what if you've got a circle and an ellipse, or even a circle and a circle, or ellipse and an ellipse? They all kind of work the same way. It looks like we have up to 4 solutions. So we could have none, 1, 2, 3, or 4, and we're just going to let the math tell us. So here we are, and we're going to have to use a different strategy this time. This time it's not going to work to substitute. It might still, but it's going to be a lot of work because you're going to need to get a square root. And you might see already another possible strategy that we had from 7.1 to solve this, which was if you take this bottom and you multiply by negative 4, and what you do to one side, you have to do to the other side, we would end up with a new equation of negative 4x squared minus 4y squared equals negative 40. Okay? We still have our original first equation. Remember, these two red equations are the same thing, just written differently. And this other one is a completely different circle or ellipse. In this case, the red one's a circle and the blue one's an ellipse. And so I'll write my blue equation underneath it. And what I'll do with those two equations is literally just add both sides. This is called the addition method, back from 7.1. And so the 4x squared and the 4x squared cancel, and we're left with negative 4y plus y squared, so that would be negative 3y squared equals negative 40 plus 13. So 13 minus 40 is 7, 20, carry the 1, 27? Negative 27, because 40 is bigger. Okay? Now y squared equals 9 if you divide negative 3 by both sides, which means y equals the square root of 9, and we introduced a square root to the problem, so we have to introduce a plus or a minus, which means y equals plus or minus 3. Well, again, we need to use the equation to find the x value, but we've got 2 this time. So we need to use both of them separately, and we need to say there's a situation where y equals 3, and there's a situation where y equals negative 3, and we need to plug and chug both of those. Okay? So if I plug and chug the y equals 3, I'll go to the left first. I'm going to use the second equation, the red equation. And the red equation says x squared plus y squared equals 10. I'd used it before I manipulated it because the numbers are smaller and might be easier for us to work with. Now we're going to plug in our 3, so we get x squared plus 3 squared equals 10, which means x squared equals, well, I can do it, plus 9 equals 10, which means x squared equals 1 if you subtract the 9 from both sides. All right, well, now we do the same system as before. We get x equals the square root of 1, and we introduce the square root to the problem. We undid a square, so we introduce a plus or a minus. And so x could equal 1 or x could equal negative 1. And so just this left side where y equals 3 introduced two solutions. So if I'm going to write my solutions out, now I've already got two and I haven't even finished the problem. The solutions, the two that I have right now are 1 comma 3 and negative 1 comma 3. And I've only done half the problem. Now I need to go to the other side and do the exact same thing with the same red equation, x squared plus y squared equals 10. And you're going to see a pretty similar argument. X squared plus negative 3 squared equals 10, which means x squared plus 9 equals 10, and we're back to where we were just a second ago. And so if we keep going, we get x squared equals 1, x equals plus or minus 1, which means x equals 1 or x equals minus 1. And so we have all combinations of 1 and 3 happening. So we also have 1 comma negative 3 and negative 1 comma negative 3 from those cases where we had the two y values, and for each of those y values we had two possible x values. And so if we look up at the top and say, well, what type of circle intersection was this? It looks like the very last one on the right, where there were 4 intersection points of this circle and this ellipse. And that was using the addition method to solve a system of equations. So we've done the substitution method and the addition method. We're going to do one more thing with this topic. And the one more thing is just graph these things and kind of plug and chug some numbers to see what these graphs look like. So you're going to notice this looks a whole lot like y equals x squared minus 1. And so I'm just going to graph y equals x squared minus 1, which is the toolkit function of x squared shifted down by 1. And so if you memorize those toolkit functions from the very first chapter of class, then you have down that this is it. The original function starts at 0, 0, goes up 1 over 1, over 2 up 4, over 3 up 9, and it's symmetrical across the y-axis. And if you're like, whoa, 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 you just graphed that parabola really fast, then you can go watch some of our quadratic equation videos where we talked about parabolas and how to graph them and how to plug and chug numbers to see where they lie. But this parabola isn't the toolkit parabola. It's actually shifted down 1. And so there's my red function. And what I'm going to do is I'm going to pick just any point on this graph and test it for the red section. So what I'm going to say is I'm going to pick, let's pick the easiest number ever. Let's do like 0, comma 2. And we're just going to see if it's true, looking at only the red equation. If we plug and chug 0, 2, is this true? So if I plug and chug 0, 2, I get 2 is greater than or equal to 0 squared minus 1, which means 2 is greater than or equal to negative 1. Is that true? Yes. And so what that allows me to do is say, okay, everything in that section, I'm going to highlight red. Everything in that section up there is a potential solution to just that red equation. I'm going to check another point outside of it just to be safe. So let's try 0 comma negative 2. So this one was a solution. 0 comma negative 2. The only thing that would change would be that negative out there. And is that true? Is negative 2 greater than negative 1? No. And so I'm not going to highlight that region. So I use those blue points to test for the red shaded area. Test for red shading. Okay, let's change colors and we'll go with green this time. Oh, that's still red. We'll go with green this time. And we'll say this looks just like a line if we do some manipulation. And so I'm going to do a little bit of manipulation first. And I'm going to say x minus y is greater than or equal to negative 1. I'll move the y over and say x is greater than or equal to y minus 1. Then I'll move the 1 over and say y is less than or equal to x plus 1. And that just looks like the regular linear function, the toolkit linear function, but shifted up by 1. And so it has a y-intercept of 0, comma 1. And it has a slope of 1, comma 1, which means it just goes up 1 over 1, up 1 over 1 for a really long time. And so I'll graph that line right there, and we'll go all the way down as well to right there. That looks like a good line for that green line. And again, we're just going to plug and chug some points to see which side they fall on. So let me try, we'll use orange to test for green. And so I'm going to plug and chug. Let's try, this point looks like it's going to be easy to plug in. That is 3, 0. All right, and we're just going to see if it makes it true or not. So if we plug in 3 for x, 3 minus 0 is greater than or equal to -1. Is that true? Is 3 greater than or equal to -1? It is. And so I'm ignoring the red line for a second. I'm only looking at the green line. I'm going to highlight orange everything in that region related to the green line. So, or I guess I could do it in green because that's how I did the last one. So I'm going to highlight this entire section in green. You don't have to do it perfect. Once you get there, we kind of get the idea. Let's check one more point to see if it's a solution. Check for green shade ink. So let's try, like, I don't know, over here. Let's do -5, comma, or what is that? 1, 2, 3, 4, 5. Yeah, -5, 0. And we'll just see. So I'm going to erase this and do it right underneath it. So there's a -5 for the x. So -5 minus 0 is greater than or equal to -1. So that's the statement. -5 is greater than or equal to -1. And is that true? -5 is greater than -1? It's not. And so we're not going to shade that region. And now that we've graphed both of those inequalities, the red and the green one, to find our solution system or all of the potential solutions to these system of inequalities, we're just going to look at what is shaded for both. And so where is the green and the red shading happening? Well, we'll make it purple now. It happens right there, and all in the middle. And that entire interval, all of the x, y points inside of that region of solutions. So there are an infinite number of x, y points in that region, and they're all solutions to this original system of inequalities. I make a quick note, because they were both greater than or equal to's, we can include not just a dotted line, but a solid line for the whole boundary of the region and of the red and the green line. If they would have been less than symbols with no underline, we would have made dotted lines. And that was the last problem of the last section of the year. Thank you for sticking with it. If you watched through all of these videos and you practice these problems, I'm grateful to you for all the hard work you've put into this class. As you approach your final exam, I would encourage you to finish the reviews and also reach out to your instructor if you need help or assistance with any type of problem. We're more than happy to help you. I mean, we like doing it. It's not just something that we can do. We enjoy doing it. We want you to succeed in this class. So thank you for watching, and I'll see you next time.